Then welcome everyone. Just for the housekeeping ahead, if you have any questions or have a question for the talk, then let us know in the chat or in the Q&A, and we will let you speak after that, so you can ask the question to Ambra directly. So now today we have our third, is it our third machine learning seminar? I think it is. And we're very happy to host Ambra Demontis. I hope I pronounced that kind of correctly. Ambra is from the University of Cagliari, from the PRALab, and has some interesting research on adversarial learning. She recently, I think, became assistant professor, because when we last time talked, that was not the case yet. And did before also a PhD at the University of Cagliari. And today she's going to talk a bit about adversarial learning. And here you are, the stage is yours.
Thank you. Yes, today I will talk to you about adversarial machine learning, which is the topic to which I have been working on since when I was a PhD student. So let's start talking about why we should care about adversarial machine learning. Machine learning, as you probably know, are algorithms that learn to perform tasks from a set of labeled examples. Nowadays, they have reached performance which are even superior to the one of human on some really specific tasks like object recognition on a famous dataset, which is called ImageNet. For their accuracy, they are therefore used in many different applications, even in applications which involve the safety of people, like self-driving car, and the security of people data, like cybersecurity, where they are used for malware detection, intrusion detection, and other applications. Therefore, the main question is, can we trust machine learning? And unfortunately, the answer is, well, no. So here we have a machine learning system which classify street signals. So when you receive the image of a stop sign in the top left, the system, it is able to correctly classify this image as a stop sign. But when an attacker adds just a little bit of noise, but that is not random, but is carefully crafted to mislead the system, we obtain the image below that, for me, and I think for everybody of you, that's still a stop sign, but for the machine learning system, it has become a yell sign. So we have a problem. Of course, an attacker cannot apply such an imperceptible perturbation to a real stop sign because that perturbation will be probably deleted from a camera which acquired the image. However, researchers have shown that an attacker can craft a perturbation which is a little bit different. So they have crafted the sticker that you see in the image on the left, those black and white stickers. So that stop sign with those stickers is misclassified as a speed limit. Therefore, those attacks can be crafted also in the real world. The attack that I mentioned, where the attacker changed the input to have it misclassified by the classifier, are called evasion attack. So let's spend a few words about how an attacker can compute this attack. So to start, let's consider a really simple machine learning system which has the task to distinguish between spam and legitimate email. So the machine learning system receives an email, for example, the spam email on the left. Firstly, it extracts the feature that in case of this system are the presence or absence of specific word in the email. Then it computes a linear combination of the feature extracted by the email with weight that you have learned before. So, for example, this classifier has learned that the word bang is usually in malicious email, so it assigns a positive weight to that word. Instead, you have learned that the word campus is usually legitimate email, so it assigns to that word a negative weight. When it receives the feature vector which corresponds to an email, it makes this linear combination, and if the result is higher than 0, it classifies an email as spam, otherwise it classifies the email as legitimate. So that's a really simple classifier. In this case, that's quite easy for an attacker to understand how we should change the spam email to have it misclassified as a legitimate email. So for example, as the goal of the attacker is to decrease the score, it is probably gonna try to hide some word which is considered as malicious by the classifier. So it can basically change some character to have that word no more recognized by the classifier. For example, here we have a 4 inside the word start and the word bang that are no more recognized. Another thing that it can do is to add some word which is considered as benign by the classifier, for example, the word campus. In this way, the attacker is able to decrease the score assigned by the classifier to the email. So in this way, it can have a score which is lower than 0 and have the spam email misclassified as a legitimate email. Now, if we would like to attack a machine learning system which is more complicated, for example, a huge deep neural network, that's not so intuitive to understand how we should change the feature, because the decision region may be more complicated and there is no clear relationship between the feature and the classifier parameter. So let's see this problem as a two-dimensional problem. Here we have a picture where we have the malicious sample represented as pink point and the legitimate sample represented as blue point. The background, that's basically the score assigned by the classifier to the point. So all the points which are in the red region are classified as malicious. All the points in the blue region are classified as legitimate. Now, how an attacker can do to have the red sample, the red malicious sample, classified as a legitimate sample? Well, we can formulate this as an optimization problem. And this way is the one which was proposed in the 2030 by Battista Biggio and other researchers from my lab. So the attacker objective function is to minimize the score, and it have a constraint because it would like to not change the spam email too much, because it should still convey the meaning, for example, the advertisement which is in the email. So it have a constraint which is represented in the picture as a diamond. And this is an optimization problem with a constraint, and we can solve this problem using gradient descent. The main idea behind gradient descent, that's really simple, and that it's basically to make a step in the deepest descent direction, so the one that decreases the score faster. So we make a step in this direction, and we ask again to ourselves, well, now which is the direction that decreases faster the score? And turn out to be this, but as you see, if we go there, we will violate the constraint. So the sample is projected back on the constraint, and we have this sample. We ask again to ourselves where we should go, and we obtain this sample, which is the one with the lower score inside the feasible domain, so inside the diamond. And as you see, this sample, it is able to evade the classifier because it is in the blue region, so it is classified as legitimate. We have used this attack to evaluate the security of a machine learning system for Android malware detection, which is called Drebin, and that was proposed in the 2014. This machine learning system is a linear classifier, a linear SVM, and it analyzes features like the permission request of the application, for example, to send SMS on internet or to use the network, some specific URL, etc. And basically, we have seen that the attacker changing just really few features, it can have the malware misclassified as legitimate. So for example, when the attacker changes two features in the malware, the 60% of the malware, it's correctly classified. All the other malware, it's no more recognized as a malware, but it's classified, is misclassified as legitimate. Now, you may think that this classifier is so vulnerable because that's a really simple classifier, right? That's a linear classifier. But actually, even huge deep neural networks are really vulnerable against this attack. So we have attacked another system, which is called Malconv, which is a convolutional neural network trained on more than 1 million features. So that's really big. And it is trained on raw byte of executable. The task that it performs, it recognizes if an executable is a malware. And we have shown that if the attacker tries to change a few bytes of the application randomly, it is not able to change the classifier decision, and we obtain this curve where we see that the evasion rate, so the percentage of the sample, the malicious sample, which is able to evade the classifier, that's really low. Instead, if we use the attack that we have seen, we have the blue curve, so we can see that when the attacker changes less than 1% of the input byte analyzed by the network, we have an evasion rate of the 60%. So that's really higher. And we should also take into account that this network is really huge, and there is something more that it's difficult for the attacker, which is the fact that one of the layers of the network is not differentiable. But you can use the same attack. You can basically approximate this layer, and you are still able to evade the classifier. There are different countermeasures that can be adopted against evasion attack, and those countermeasures can be categorized in two categories. One is robust optimization. So basically, the defender tries to inject in the learning phase knowledge about the fact that the system will be attacked and about the attack that he expects that the attacker is going to do. And the other family is the rejection or detection of adversarial example. I will show you some example about both. This is the first, and it belongs to the first family, so the one which try to improve the learning algorithm, basically. In this paper, we have tried to increase the security of Drebin, which is the linear classifier which detects Android malware that we have seen before. And as I said, that classifier, that's a linear SVM. So as you probably know, the loss function optimized by a linear SVM, it's basically made by two terms. One, which is this, that basically try to make the classifier learn to classify really well the sample that the classifier see during the training phase. And there is another term, which is called regularizer, that try to make the classifier able to work well also on samples which are a little bit different from the one that you see during the training phase. Now, the problem of a linear SVM, when we consider its robustness against this kind of attack, is that this classifier gives a lot of weight to just really few features. So for the attacker, that's easy to evade the classifier because modifying just few features, it can change a lot the decision of the classifier, because change a lot the score. So what we have proposed is to change the regularizer. So instead of using an L2 infinity norm regularizer, we have proposed to use an L infinity norm regularizer. Why we have chosen this norm? Well, because it enforces the classifier to learn weights which are evenly distributed. So for example, in this plot on the right, we see the weight of the linear SVM, and we see that it gives a lot of weight to just few features. While we have the weight of the SVM classifier, which is the one that we have proposed, which are depicted in red, and we see that the classifier gives weight to a lot more different features, and it gives a lower weight to each feature. So basically, the attacker, to change the score, have to change more features. In fact, when we evaluate the security of this classifier, we see that it is really more robust. So in the plot on the left, we see the security of the classifier, the original classifier, which is the green curve that we have seen before. So we see that the detection rate drops to 60% at the 1% of false positive when the attacker changes just 2 features in the malware, while the SVM have the same detection rate when the attacker changes 15 features. So that's really more robust. And you have to consider that for an attacker, that's not so easy to change feature without compromise the malicious functionality of the malware. So it may be difficult if you have to change many features or even impossible. Now, the other family of countermeasure, I said that is the one which tries to detect and reject adversarial example. So the main idea behind this countermeasure is that often adversarial examples occur in regions where there are no training samples. And those regions are called blind spot. So for example, here we have some original sample of the red class, which is modified by the attacker. And the sample here is able to evade the classifier and be misclassified as a blue sample. So the idea behind this countermeasure is to enclose the legitimate classes. So in the right plot, everything, it is in the white region, it is classified by the classifier as an attack. As you see, we pay some false positive because we have some blue sample, and the same for the other classes, which is in the white region. So it means that we are classify some real legitimate sample as an adversarial example, but in this way, the attacker isn't forced to change more the malicious sample to have it misclassified, and the malicious sample to be misclassified has to be really similar to the training sample of the class that you would like to be predicted, at least in the feature space, which is the one analyzed by the classifier. So how you can create a classifier which have a decision region like this? Well, we have proposed to remove from a deep neural network the softmax and substitute it with an SVM with an RBF kernel. Well, why we have chosen this classifier? Because it has a property which is called compact abating probability. So basically, the classifier, when receive a sample, if the sample is near to the training sample, the classifier is confident in its prediction. So we will have a class which will have a really higher score respect to the other classes, like the class cap in this example. Instead, if the classifier receives a sample which is far away from all the training sample, it will be not confident in its predictions. So we will have a similar score for similar and low score for all the classes. So using this classifier, we can basically classify as adversarial example all the sample for which the score of the class, which a higher score, is lower a certain threshold. So we classify those samples as attack. More recently, we have proposed to modify the architecture of this classifier, proposing this classifier, which is called deep neural rejection. And the underlying idea is that in the other classifier, basically, we were rejecting all the sample which was far from the training data in the feature space given by the last layer of the network. Here, we try to reject all the sample which are far from the training sample, not only considering the feature space that we get if we analyze the output at the last layer of the network, but also if we analyze the previous layers. So basically, we have more information to reject the sample. We have to compare the performance of both this classifier, or better, the security of this classifier on two datasets which are really famous and are the MIS dataset, which is a computer vision dataset which basically contain a lot of different digits, the image of a lot of different digits. And we have used also the CIFAR10 dataset. And we see that on both the dataset, the DNR, so the classifier which analyze more layer, that's more robust respect to the one which analyze just one layer. For this comparison in this experiment, we have analyzed 3 layers. You may obtain something better if you analyze more layers. But the problem is that this classifier, as we have proposed it will become really slow at test time, because if you consider more layers, you are basically adding more SVM RBF. And the problem is that each SVM, when receive an image, it compares that image with all the support vectors, which are basically a subset of the training image. And when the dataset is large, those support vectors are really a lot. So something that you can do to speed up this classifier is to enforce each SVM to use less support vector, which is something that we have proposed in the 2016, was not proposed against adversarial example, but that's something that may be useful to speed up this classifier. And how you can do, well, basically, you fix the number of support vector that the SVM can use, and instead that taking those support vector from the training dataset, you optimize the support vector. So in this way, you are basically able to use really less support vector, because optimizing them, you are able to summarize the information that you add in the original set of support vector in really few support vectors. So for example, you can go from 100 or even more, 1000 support vector to just 20 support vector, and you have the same accuracy. So,
Ambra, can I interrupt you at this point? Thank you. Because
yes.
we have 2 questions, and I think one we missed, it was earlier. So since we're at this slide, and there was a question for this slide, questions from Thomas.
Sweet.
What is the epsilon on the graph on this slide? Yeah. What is the epsilon on the x-axis?
That's basically the perturbation that the attacker inject in the L2 norm. Okay. Thank you, because I forgot to tell it.
And the perturbation is some kind of random noise, or should I let Thomas ask more if you want? But I'm asking.
That's noise, but that's carefully crafted by the attacker with the attack that we have seen before.
Mm-hmm. Okay, thank you. And I think Michael Whitbrook had one question earlier.
But maybe we can.
So...
My question is not important. I would have raised it for the web.
Okay, good. Well, then we are done. Yeah.
Okay. So another countermeasure that we have proposed, which is based on rejection, is the one that we have proposed in this paper. And basically, it tried to exploit domain knowledge. So in this case, we have the real classes, which in this example are cat and motorbike. And we have some additional class, which in this example are the class vehicle and animal. So we have a multi-class problem, basically. This approach converts the domain knowledge in constraint. So in this example, we have the constraint that we see here, which are a cat should be also an animal. if a sample is classified as a motorbike, it should be classified also as a vehicle. If it is a vehicle, it should not be classified as an animal. And if it is an animal, or better, it may be an animal or a vehicle, not both. And basically, we use those constraints to enforce the classifier to learn a more sensible mapping, because it will try to separate, for example, all the animal from the vehicle, and it is able to exploit the knowledge even from unlabeled examples that are represented in this image as a gray triangle, because it doesn't know the label, but it knows that, for example, if it predicts that a sample that's an animal, it cannot be a vehicle. So it can, during the learning phase, adjust the decision region in the way that those constraints are satisfied. And we use those constraints also to reject samples. So for example, the malicious sample in violet is rejected because it violates some constraints. So for example, because it's predicted by the classifier as a vehicle and also as an animal. So we have seen a lot of countermeasures, a lot of different countermeasures against evasion. Now the question may be, well, are defended systems secure or not? And well, unfortunately, they are not. They are more secure, but they are still not really robust. For example, in computer vision, we are still far from the ability of human to recognize example in the presence of adversarial noise. Here we see some example on two different datasets. The MNIST dataset, so a dataset with digit on the left, and a dataset that that have a lot of street signal on the right. So we see that when we try to devise some adversarial example against a classifier which classify the MNIST datasets on the one with digit, we see some violet point, which may be strange, but I think for everybody, those samples are still a 6 and a 2, while for the classifier, they are not. And this classifier is a classifier which has been proposed in the 2019 at NeoRIPS, which is one of the top machine learning venues. And if we consider the same classifier, but that this time has been trained on the dataset which contains street signals, well, the situation is even worse because we are not even able to see perturbation on the samples. So we are still far from the ability of human to recognize image. Now, the attack of which I've talked about were evasion attack, but there is another attack that may be perpetrated against machine learning system, which is called poisoning. So here we have basically the pipeline of a standard machine learning system that receives training data, extract the feature. We learn the classifier, and this classifier, hopefully, at least, will classify well also the test sample. The poisoning basically corrupts a part of the training data so that it maximizes the error of the classifier on test data. So here we have an example on a classifier which distinguish between dog and fish. in the top left, we have a training set image, which is the image of a dog. So basically, the attacker, firstly, it flips the label. So it said that the label of this image, it's fish. Then it had some carefully crafted noise, which is carefully crafted to maximize the error of the classifier on the test sample. So when the classifier, it is trained on the training dataset plus this poisoning point, it is no more able to correctly classify a lot of test image, as we've seen in the row below. So for example, when it received the image on the left that was correctly classified as a dog with an high confidence, it said, that's a fish, and I'm confident at 90-17% that is a fish. And the same for the other image that you see in the row below. How you can compute poisoning sample? Well, in the 2012, from Battista Biggio and other researchers from my lab, they proposed to formulate this problem as an optimization problem, like they did for the evasion sample. And here, basically, we see that the objective function of the attacker does find a point XC that maximizes the loss of the classifier on a dataset, which is different from the training dataset, because its goal is to increase the loss on the test data, but it doesn't really know the test data that will be used from the classifier. So it uses a different dataset, a validation dataset. But the solution of this problem depends on the classifier weight, which in turn depends on another problem, which is called inner problem, which is basically the learning problem. So find the weight that minimizes the error of the classifier on the training sample, plus the poisoning point, because the attacker injects those points inside the training set. This problem can be solved using gradient descent, but to do this, you have to compute the gradient of this loss function respect to the point. So basically, what was proposed as a solution to compute the gradient was to replace the inner problem with the equilibrium condition. So you take the equation, you substitute the equation, and you are able to compute the gradient, basically. The author tested this approach considering a linear SVM trained on the MNIST dataset, trained just to recognize 0 from 4, and they obtained the image in the center of the slide, which is the poisoning image, and when they add this image to the training set, the error, the classification error, goes up to the 20%. So that's a really effective attack. And if you inject more points in the training dataset, more poisoning point, the situation is even worse. So for example, they inject the 8% of the training dataset, and they were able to increase the test error almost to the 40%. A bit less, but that's still a lot. Now, if you would like to attack a huge neural network, you cannot use basically the trick that they proposed, so to replace the inner problem with the equilibrium condition, because if you do this, you will have to invert a matrix, and this operation will be cubic in the number of parameters of the classifier. So if you have a huge deep neural network, well, if you work at NVIDIA, so you have a really powerful hardware that you can use, you may think about this as a solution, but otherwise that's simply not feasible. So you have to find another approach. And a solution that may come up to your mind is to use automatic differentiation, which is basically the technique that is used by TensorFlow, by PyTorch to train deep neural network. So automatic differentiation basically construct a graph with a node for each basic operation that you make to compute the function, and then it computes the gradient of each basic operation and aggregate the results using the chain rule. So here we have the graph that you have to construct if you would like to map the dependency between the function of which you would like to compute the gradient, so the loss on the validation dataset, with the variable respect which you would like to compute the gradient, which is the poisoning point. As you see, there is all the learning procedure that you have to map in memory. And the problem is that in each iteration of the learning procedure, you update all the network weights. So basically, if you try to do something like that, you have to replicate the structure of the neural network in memory t times, where t is the number of iteration of the learning procedure. So it will be really memory expensive. So what we proposed to do was to use an optimization technique, which is called backgradient optimization, that it's really similar to automatic differentiation, but it exploits the knowledge that the operations that are made during the learning procedure are always the same. They are only applied to a network with different weight. So it stores the operation made during a single iteration, and it uses an iterative algorithm to basically reverse the learning, so get the weight that you need to that computation on the fly. So that's sufficient to store the neural network in memory just once. We have tested this attack against shallow classifier on two different datasets, a spam-based dataset, which basically contains malicious and spam email, and on a dataset which contain benign application and ransom, which are basically malware which ask to you for a ransom. And we see that that's really effective, because injecting just a little fraction of point into the training data, the test error goes up a lot. We have made also a proof of concept experiment against deep neural network. We have crafted really few points, 10 out of 100 used to train the deep neural network. And in this case, it seems secure. Well, the error didn't increase in this little experiment. Of course, to understand if they are robust, we need a more extensive investigation, a more extensive experiment. Against poisoning as well, there are two family of countermeasures, which are basically the same that we have against evasion attacks, so robust learning and data sanitization, which is try to detect and remove, in this case, training data from the training data set. The idea behind data sanitization is that usually the poisoning points tend to be outliers. So, for example, here we have a poisoning point. I mean, in the left plot, we have the poisoning point XC, which is the optimal poisoning point computed against this linear SVM. And we see that it is really far away from the training data set. And we have the same for an RBF SVM on the right plot. And again, we see that XC, it's really far from the training sample, which are the red and blue point in the center of the plot, basically. So removing the outlier, you are able to remove a lot of poisoning points. Another countermeasure that you can use is to increase the regularization of the classifier. So for example, here we can see the accuracy of a linear SVM in blue in two versions. One which is evenly regularized, which is the line, the dotted line, and we see that the error, even if we add a fraction of poisoning point equal to the 20%, the error doesn't increase much. Instead, if we do the same for a linear SVM, which is not really regularized, we have the solid curve, the solid blue curve, and we see that the test error is much higher in this case. Something which is interesting is to understand if the attacker has to be a lot of knowledge about the system, because all the attack of which I talk about, in all the attacker had a perfect knowledge of the system that it was attacking. But usually, for example, if we would like to attack an antivirus, well, probably the company will not share all the detail about the system. And in this case, the attacker can leverage on a property of the adversarial example, which is called transferability, which is basically the ability of an attack crafted against a machine learning model called surrogate to be effective against a different machine learning model. In this paper that we have presented at Usenix in the 2019, we have analyzed which are the factors which have an impact on transferability, and they are different, but they are all related to the classifier complexity. The main takeaway are that, as we have seen also from the slide, machine learning systems which are evenly regularized are more robust against evasion and poisoning. Instead, from the attacker point of view, the main takeaway is that if the attacker would like to craft an evasion attack, the best surrogate that he can choose, that's a surrogate which is evenly regularized. Instead, if we would like to compute a poisoning attack, the best surrogate is the one which have a similar level of complexity of its target. So there are different open problems regarding the security of machine learning system. And one which regards evasion is, well, how we can construct machine learning systems which are secure against evasion. And when I talk about security, it depends on which domain we are considering. For example, if we consider security, it means that we have a machine learning system for which it is impossible for the attacker to craft a malicious sample which have malicious functionality, but is misclassified as legitimate. And the challenge is to make this having a system which is highly accurate and avoiding to basically select the feature manually. If we consider computer vision, security means make the machine learning system avoid errors that humans do not do. And that's another problem, how we can do. Maybe we can try to make the system work more as humans. So we can try to make a system which is biased toward the detection of shape rather than the detection of texture as humans are. Or we can add some constraint, but it's still to be understood how we can construct a secure machine learning system. Regarding poisoning, instead, an interesting open problem is that, well, we know that deep neural network with high capacity tend to overfit the training data set. They are even able to fit perfectly with 100% of accuracy, completely random noise. So the problem is that as they have a decision region which is really detailed, are they secure or not against poisoning attack? Because it may be the case that the decision region change just in the region where you inject a poisoning point, but doesn't really change a lot. So the classification of the test sample may be really similar. Finally, I would present you open source Python library, which we have released and it's freely available in the website, which is written in this slide. And it's called SecML, and it may be useful for you if you work, of course, on adversarial machine learning, but also if you have a classifier and you would like to understand which is its security against evasion or poisoning attack. So this library contains a lot of attack ready that you can run on your machine learning system. And it have ready plot that you can use to plot with few line of code the security of the classifier. And moreover, it has some explainability technique that you can use in case your machine learning system turns out to not be robust, to better understand why it is not robust. So that's everything. If you have any more questions, I would be pleased to answer.
Thank you. Thank you for your talk. I think we missed one question earlier, so I will should we let Qming, or sorry if I'm pronouncing right, to ask it, or?
Yep, if he wants, so he should be able to talk now.
Okay.
Yeah, can you hear me?
Yes.
Yeah, just a question on page 28. So yeah, just how to define that domain knowledge. So is it like a predefined domain knowledge, or it's trained by some unsupervised learning method? So for this cluster.
Okay, so well, you have a mix of sample for which you know all the labels. So for example, you have 0, 1 for cat, motorbike, vehicle, and animal. So for the true classes and also for the secret classes. And you may have also a part of the training data set for which you doesn't know all the label. You may know, for example, just that that sample, it is a vehicle. So you have some sample which is partially labeled, or you can even doesn't have any knowledge, any label about that sample. So in that case, you can still use that sample during the training phase, because you can try to get the prediction of the classifier for that sample. So you will receive basically a label, I mean a value for each label. So for all the 4 labels. And you can see if this prediction respect or not the constraint. So you can adjust the decision region of the classifier in the way that you have also the sample for which you doesn't have the label, but they should be classified in a way which respect the constraint. So you basically, when you train the classifier, you have a loss for the constraint which are not satisfied. And you have a penalty that you have to optimize along with the standard function that you optimize usually during learning.
Yes, thank you. Can you put the paper on the page 28? So put the paper link on the chat area. So I think it's probably interesting to towards the common sense reasoning. So I think it's probably interesting so for example, the cat can be derived to animal. So it's just for machine and model to understand. So actually cat is kind of animal. So sort of the common sense reasoning, I think this like the symbolic representation can be helpful to towards the real common sense reasoning. So yes, thank you for your explanation.
Thank you for your question.
Luke has a similar question. Should we let him ask? Luke, do you want?
But it was more of a request than really a question.
Yeah, it's more like first, I'm actually a big fan of one of your papers. The why do adversarial attack transfer. So yeah, I kind of studied 2 of your paper. Another of your paper I'm actually very interested in the Android malware detection paper. So yeah, thank you so much. I'm looking at the page 23 and then the page 28. Quite interesting in both of those. It's kind of like a different direction. So could you just provide the full title of those papers? Thank you.
Of which one?
Page 23 and then the page 28.
Okay.
We can
We
share.
can do that
well,
offline. Mm-hmm.
Okay.
Yeah. We can send an email around. I mean, we will publish the recording of this anyway, and we can send to everyone. Share also the paper names. Yeah.
One more question from Hamid, or I'm not sure if I'm pronouncing correctly. We can let you ask the question. Jörg, can you?
Yep, he can already speak.
Okay. Yes, please. Nobody wants to?
Nothing.
Hi.
Hi.
Thank you very much for your interesting talk. I have a question about in some slides that you were talking about evasion attacks in the domain of malware detection. Actually, as you know, one of the challenging evasion attacks in the software domain is keeping the functionality of malware. As far as I know, the majority of methods use some strategies that are based on feature space stacks, but the problem is keeping the functionality of malware. I would like to know what's your idea and what's your solution for keeping the functionality of malware in the in software domain.
Okay, well, in the attack that we have devised to test the security of SecSVM, we have basically made the malware just in the feature space, okay? So the classifier may be even more secure against an attack which craft real malware. Because as you said, in that case, the attacker has to take into account more factors, because it should avoid to break the malicious functionality, but also it would probably avoid to inject, I mean, some feature which is not coherent with the rest of the code, so that may be found easily. So here, for example, we were adding features which is easier for the attacker because it usually doesn't break the malware, but it may create artifact in the malware. A solution has been proposed not by me or by my research group, but it has been proposed by the group of Lorenzo Cavallaro, Fabio Perazzi, and other researchers, and was basically to compute an attack which take into account the constraint in the problem space. There is a really nice paper about this. I can send you the reference of this paper.
I read this paper. I mean, actually, I would like to say that it seems focusing on problem space attacks is more promising in comparison on feature space attacks. What's your idea?
Can you please repeat the question?
I mean that it seems in the software domains, for example, for detecting malware, it seems that focusing on problem space attacks is more interesting or more promising in comparison feature space attacks. I mean that because feature space attacks have feature space attacks have some challenge, as that one of them is keeping functionality. I would like your idea about this approach.
I think that if you are an attacker, of course, you have to compute the attack in the problem space, because you would like to have something which you can realize. So you would like to have some malware that you can really construct. If you are a defender and you use the attack just to evaluate the security of your machine learning system, that's less important, because if you consider attack crafted in the feature space, you are basically considering a case which is even worse of the one that you are gonna face. So, of course, I mean, you may devise a countermeasure which may exploit the knowledge of the fact that some specific feature cannot be changed. So in some way, considering more the problem space. So for example, in the case of this classifier, you may give a penalty which is higher to the feature that the attacker can change easily, so that the classifier basically tend to give a lower weight to the feature that the attacker can change easily. But this is what has been done so far. That's still to be understood, how you can exploit in the learning problem more knowledge about the problem space. That's still something that has to be investigated. That's another open problem, basically.
Thank you very much for your answer.
Thank you.
Okay.
I don't think we have other questions. Is there any other question left to be asked? I guess there are always questions to be asked.
But also the time is running out, and people,
The
at least in
time is
Auckland,
running
is
out.
getting
That's
late.
true. Yeah.
So I guess we kind of let me.
So yeah, we're coming to the end. Then thank you, Ambra, once again for your talk and for wanting to join us early in the morning in Italy, if I'm correct. So yeah, have a nice day and working week, and we'll be in touch. We use this opportunity also to thank everyone for joining us and also inviting you for our next talks. This week actually is nice. We have a second talk coming. This talk is not a virtual talk. It's actually on campus talk on Wednesday. So in the old government house. So please come for Karatiana Tayuru. Sorry, I didn't pronounce it well. A Maori researcher, which researches about data ethics and in particular Maori ethics and cultural considerations with artificial intelligence, algorithms, data, and so on. And in a month, actually, we will have another virtual machine learning talk. And our guest will be then from Chinese University, Philippe Fournier, Vigor, which will talk about challenges of automatic discovery of interesting patterns in data. So thanks all for joining us, and have a nice evening and have a nice, not morning, but day back in Europe. Thank you. Bye.